Hi folks, I'm Chris King. I'm retired from teaching chemistry at Troy University. Surface tension is fascinating, but what causes it? That will be approached scientifically. Do experiments, look at the results, form a hypothesis, and test the hypothesis. The first experiment is a sliding wire demonstration. The sliding wire apparatus is a wire framework in the shape of a rectangle to which is loosely attached a sliding wire. This wire can slide the whole length of the framework. The apparatus will be dipped in soapy water. A film forms on both sides of the wire. When one of the films is punctured, the other film pulls the wire to the other end. This pull is called surface tension. Can it pull the wire uphill? This is maybe a 30-degree angle here. It did pull it uphill. Surface tension can pull this wire almost vertically, though not so smoothly. I used my finger to poke this one, maybe a 70-degree angle. And it did indeed pull it vertically. The sliding wire assembly demonstrates that surface tension involves a force. This force is an inward pull on the film, and from the videos, it's a pretty strong force. For figuring out the cause of this force, a representation of the sliding wire assembly will be used. The sliding wire is shown as round because it's being viewed from the end. On each side of this wire is a soap film. Using this representation, a hypothesis will be given. In science, a hypothesis is a tentative explanation. So the tentative explanation of surface tension is that the force, the inward pull, results from attractions between molecules in the liquid. If that's the case, the force is distributed throughout the thickness of the film. The molecules pull on both sides of the sliding wire. When one of the films is punctured, the other film pulls on the sliding wire, moving it towards the end of the apparatus. Next, this hypothesis will be tested to see if it's consistent with other experimental observations with the sliding wire. These experiments will also illustrate other properties of surface tension. The learning objectives for this section are: describe the effects of film length and film thickness on surface tension. The effect of film length will be examined first. The inward pull of surface tension exerts a force on the sliding wire. The inward force of the long film pulls the wire up. At the same time, the inward force of the shorter film pulls the wire down. The result of these two forces is that the wire doesn't move. What does that say about these forces? They are equal. That's why the wire doesn't move. The long film and the short film both exert the same force on the wire, leading to the conclusion surface tension is independent of the length of the film. When a spring is stretched, the more it's stretched, the stronger it pulls back. Surface tension isn't like that. No matter how long the film is, the pull is always the same. Next, the effect of film thickness will be examined. The sliding wire will be moved up using tweezers. That stretches one film so it gets thinner. And it squishes the other so it gets thicker. Now, when the tweezers release the wire, will it move up, move down, or stay where it is? Based on the previous hypothesis, it'll move up because more molecules are pulling on the wire since the film is thicker. Let's see. The tweezers let go of the film and it stays where it was. The wire didn't move. Although one film is thicker than the other, the forces on the wire are still equal. indicating that surface tension is independent of the thickness of the film. That is not consistent with the hypothesis. When tweezers were used to move the wire, one film got thinner and the other thicker. As the film gets thicker, the liquid attractions to the wire would increase because more molecules are pulling on the wire, so the attractive force on the wire would be greater on the thick side than on the thin side. The result would be that the wire moves towards the thicker side, if that explanation were correct. But that's not what happens. A modified hypothesis is that the main attraction in the film is in the surface layers. A surface layer is on the top of a thick layer, and it has an inward pull within that layer, according to this modified hypothesis. Likewise, on the bottom, and the thin film has identical surface layers. Although the thickness of the two films are different, all four surface layers are the same. They all have the same inward pull. Consequently, the surface layer attractions cancel, so the wire doesn't move. The bulk liquid is taken to be separate from the surface layers. The attractions within the bulk liquid must be pretty small because the film thickness has no effect. The modified hypothesis can be stated as the attraction between molecules is much greater in the surface layer than in the bulk liquid. This conclusion raises a question. How can the attraction between molecules be greater on the surface? Explaining that is the task of the molecular explanation. The molecular explanation requires understanding the forces between molecules, but that requires understanding the forces within molecules. So, covalent bonding forces will be presented first. Here's the learning objective for this section. Suppose two covalently bonded atoms are at their equilibrium separation. Describe the strength of the force holding them together. Fluorine will be used as an example. It has 7 valence electrons in its Lewis dot structure, giving it an unpaired electron. The 4 groups of electrons can be placed into orbitals. That unpaired electron will be involved in bonding. In 3 dimensions, the 4 orbitals would be in sp3 hybridized orbitals. The unpaired electrons from 2 of these atoms can combine to form the difluorine molecule. All molecules vibrate, which changes the internuclear separation, the distance between the nuclei. There is a particular separation called the equilibrium separation that can be explained with a plot showing how the potential energy changes as the internuclear separation changes for difluorine. So the potential energy changes as the molecule vibrates. The equilibrium separation is the separation at the potential energy minimum. So these 2 atoms are at their equilibrium separation. At that separation, the potential energy is minus 160 kilojoules per mole. This is relative to 0, but what does 0 refer to? Well, as the atoms get further apart, the potential energy gets less. The potential energy is defined to be 0 as the internuclear separation approaches infinity. So that minus 160 kilojoules per mole is how much energy it takes to completely separate 2 fluorine atoms. The cause of the potential energy minimum can be understood by looking at the forces holding a molecule together. Molecules are held together by the interaction between like charges and opposite charges. The nucleus has positive charges, just one is shown. An unpaired electron can be envisioned to be in an orbital on the atom. If a second atom is present, the atoms will be attracted by the opposite charges of the nucleus on one atom and the electron on another. The green lines represent the attractive force between opposite charges. This attractive force becomes more attractive as the atoms get closer together. The units of force are given in petanewtons per mole. In computer storage, there's kilobytes, megabytes, gigabytes, terabytes, and after that, petabytes. The capital P is for peta, 10 to the 15th power. If only attractive forces were present, the atoms would coalesce into one. They don't coalesce because repulsive forces are also present. These come about because like charges repel. There is repulsion between the nuclei and between the electrons. The repulsive force becomes more repulsive as the atoms get closer together. Adding the attractive and repulsive forces together gives the total force, or net force. The learning objective was to describe the net force at the equilibrium separation. It's zero. This is weird. It takes energy to break the bond, but the force holding the atoms together at equilibrium is zero. Now, if squeezed together, repulsion increases. If pulled apart, attraction increases. But at equilibrium, nothing. I've been saying that the triple bond in dinitrogen is strong. But what's really meant is it takes a lot of energy to break that bond. A bond with zero force is hardly strong. The forces within a molecule have now been reviewed. Next, the forces between molecules will be described using London dispersion forces. The reason for using London dispersion forces to explain surface tension starts with this. The surface of a liquid has an inward pole. Because the surface is covered with molecules, that inward pole must be between molecules. Between molecules means intermolecular. Examples of intermolecular forces are dipole-dipole forces and London dispersion forces. The reason for focusing on London dispersion forces is that London dispersion forces are present in all substances, even polar molecules. If surface tension can be explained in a substance with only London dispersion forces present, then the explanation in polar molecules should be similar. London forces will be illustrated using argon because the only attraction between argon atoms is from London dispersion forces. Also, although argon is normally a gas, on cooling it does form a liquid. Its normal boiling point is 87 Kelvin, and that liquid has surface tension, which has been measured. Here's the learning objective for this section. Suppose two molecules are initially at their equilibrium separation. As the separation between them increases, describe how the attraction between them changes. The starting point is, again, a plot of potential energy versus separation. The plot is of London dispersion forces for two argon atoms. The shape is very similar to the plot for covalent bonding. However, the potential energy minimum is only about -1 kilojoule per mole for this intermolecular attraction. That's much weaker than the energy of a covalent bond, which is -160 kilojoules per mole for difluorine. Just as forces in covalent bonds are explained with charges, so too are London dispersion forces. The little red circle represents the nucleus of an atom. It is surrounded by a cloud of electrons. The electrons are moving and can form an instantaneous dipole. This produces a partial negative charge on one side of the atom and leaves a partial positive charge on the other side. This instantaneous dipole induces a dipole in a nearby atom. The opposite charges attract. The nearest opposite charges have a bit stronger attraction than the more distant pair. This attractive force is called the London dispersion force. The units of this force are given as teranewtons per mole. That's 1,000 times less than the petanewtons per mole given in the covalent bonding example. This is an attractive force. A repulsive force must also be present so that the atoms don't coalesce. The same repulsion present in covalent bonding is acting in intermolecular bonding, that is, repulsion between electrons and the nuclei. But London dispersion has an additional repulsive component, which is due to the repulsion between the like partial negative charges and the like partial positive charges. These repulsions become stronger as the atoms get closer together. The combination of the repulsive and attractive force is the net force. The net force is, again, zero at the minimum in the potential energy. The learning objective for this section is to know the trend in force, starting from the equilibrium separation. As the separation increases, the net force first becomes more attractive, then less attractive. The main idea for understanding surface tension is that as the separation between two molecules increases, the attraction between them first increases, then decreases. This applies to nonpolar atoms and molecules. This trend is also expected to apply to polar molecules because of the similarity of London forces and dipole-dipole forces. London dispersion forces involve an instantaneous dipole in one molecule inducing a dipole in another. Dipole-dipole forces involve a polar molecule which has partial charges on it, giving it a dipole. That molecule is attracted to another polar molecule. The difference between these two forces is that London dispersion forces involve temporary dipoles, whereas dipole-dipole forces involve permanent dipoles. When the polar molecules are at their equilibrium separation, the attraction is zero, because repulsive forces keep them from coalescing. As the separation between them increases, the attraction between them first increases, then decreases. With this background, the molecular explanation of surface tension can now be given. The molecular explanation of surface tension is an increased attraction between surface molecules caused by increased separations of surface molecules. How absurdly simple! A learning objective for this section is describe the range of intermolecular separations that can produce an attractive force that is greater than in the bulk liquid. To describe where a force is greater than in a liquid requires first knowing what is the force in the liquid. Argon will again be used as an example. The molecules in a liquid are confined by their neighbors, so their internuclear separations are near the equilibrium separation. However, those molecules have some thermal energy. Consequently, the liquid molecules are a little further apart than the equilibrium separation. So the range of separations where the attractions are greater than in the liquid is between that red star, where the attraction is increasing with increasing separation, and the red dot, where the attraction is decreasing with separation. Between those 2 points, the attraction between molecules will be greater than in the liquid. Suppose some of the top atoms are removed. Maybe they boil away. Then an atom that was formerly in the bulk liquid becomes a surface atom. Being on the surface, that atom can move further away from its neighbors. The green bond indicates that the separation from its neighbor has increased, and since its internuclear distance has increased, its attraction for that neighbor has increased. If the separation had been less, or even less, the attraction would be greater and the surface tension would be larger. That is the molecular cause of surface tension. Here is a related learning objective. Explain what mainly causes surface molecules to be more separated from each other than are molecules in the bulk liquid. The explanation is separations increase mainly because surfaces have molecules on just one side. In the bulk of the liquid, only a few molecules are separated enough to have extra attraction. Those are shown by the green lines. But if some molecules are removed to produce a surface, then the surface molecules have more freedom of movement. And they can get further apart, resulting in increased attraction on the surface. The main cause of surface tension is that molecules at the surface have more freedom of movement since they have molecules on only one side. This figure shows a string of 3 surface molecules with extra attractions between them. Such chains of attractions tend to not be very long because the separations between surface molecules are constantly changing. In other words, the extra attraction between any pair of surface molecules doesn't last long. This constant change means that there is a dynamic aspect to surface tension. The learning objective for this section is describe the dynamic aspect of surface tension. Here's a description and explanation. The attractions between surface molecules are constantly changing because their separations are constantly changing, because they are constantly moving. This can be illustrated with a molecular view of a surface. A glass of wine has a surface. Here's a top view of that surface. Imagine a small area of that surface gets expanded into a molecular view. The gold spheres represent the wall. The blue spheres represent the surface. The green lines indicate the increased separations and attractions. These separations between molecules are constantly changing. This represents an initial arrangement of attractions between molecules. This is a later arrangement of attractions. The dynamic aspect of surface tension is that the attractions between molecules are constantly changing because the positions of the molecules are constantly changing. Here's the initial view again, and the later arrangement again. The surface can be thought of as having tiny regions of attraction, which can be found by tracing the green increased attraction bonds. Some of these regions are pulling on the wall, creating the pull of surface tension on the wall. Since each region contains only a few surface molecules, the region of the surface that pulls on the wall is only a few molecules thick. That is consistent with the observation that surface tension is independent of the length of the film, or in this case, the surface. I hope you've enjoyed this video. Please leave suggestions or concerns in the comments. On my website, christopherking.name, is a note on how to construct and use a sliding wire assembly. A second video on surface tension is being worked on. Bye.